All right, so this is a thermo-entropy question. Hopefully the audio quality is good enough. And let's start this. So the givens are, step 1, rewrite the givens. Let's highlight this. Now, I think I'll talk more quietly. Oh, come on. 30 kilogram iron block. Here's 30 kilograms. 30 kilograms, 30 kilograms. Sorry, there's no cursor on this. 80 Celsius. Both are at 80. Let's write that down. ADC. ADC. Stuff's dropped into a large lake at 15C. Hooray. Q goes out. Q goes out. Q is heat. So the question is, so this, afterwards, thermal equilibrium is reached, and you need to find the total entropy change, which means you have to find the entropy here, the entropy change of the iron, entropy change of the copper, and the entropy change of the lake, which is the final goal. Well, actually, the entropy change for the whole process. Whoops, my bad. So, first you set a boundary. The boundary is here. Let's copy that. And erase some stuff. So here is the boundary. Dot, 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 dot. There's no volume going in or out. And I would say just imagine that these at some point don't exist before equilibrium. This is a infinite, the water lake is an infinite, what do you call that? Heat reservoir. Infinite heat reservoir. Meaning that it stays at 15C Celsius, centigrade, whatever it's called. And at some point you need to convert that to Kelvin. Let's use the estimated 273.14. So you could skip the 14. And I don't like black, so let's use dark blue. No, I don't even like dark blue. Let's use purple. So that converted to Kelvin is some basic thing. 788 Kelvin. That's the estimated temperature of that. And then for the other things, we'll do that later. So first, you start off with a problem. The first thing that you do, whoops, I don't want to copy that. The first thing that you do is reread the question and understand what it's saying. The second thing that you do is, I guess, restate things and state your assumptions for the thermodynamic system. So, assumptions. I was thinking I would type, but I'm not going to type. Gotta make some coughs. Assumptions. Assumption number 1. Water is incompressible. Everything's simplified. Everything's incompressible. Including the water, the copper, which you say is Cu. Whoops, not uppercase. And iron, which is Fe. Otherwise, let's just use H2, that's basic. Cu is copper. I'm just going to write copper. Cu would be faster, and iron. I forgot if some people say iron or something like that. So assumption 1, incompressible. The water, copper, and iron are incompressible. I assume you could have a compressible block, but then there would be negligible, the error, if you take into consideration how much the copper over here and iron compress, then there's going to be a marginal error. Assumption number 2, the states are both at equilibrium before and after. Whoops, that's not 2. So what does it say? Here, top left, thermal equilibrium is reached. And here, these blocks that are at 80 C are dropped into the lake. So before, just imagine that you have this block of water. Before, there's just water everywhere, red stuff. You know what? Let's not make it red. There's water everywhere. So this is before, and then temperature's at 15 C. And afterwards, here, let's erase everything. This stuff just teleports in at equilibrium at 40, I think it's 40 C. Is it 40 C? 80 C, both initially at 80 C. So those things teleport in, and there's no kinetic energy. They're just sitting on the ground over here inside the water, inside this infinite reservoir that stays at 15 C. So there's no change in, there's no kinetic energy, and there's no change in potential energy. Whoops, that's not a P. Assumption number 3 is what? The lake is an infinite reservoir that doesn't change temperature. The lake doesn't change temperature. That's all you need to say. It stays at 15 C. Number 2, part 2 is, so we're basing this off of, I think, a Cengel book. Let's see what the book is. Thermo book. Loading. We're on page 355. Let's see. Page 362. Let's write that down. I don't even have a pen over here. 362. Let's go to page 1. Thermodynamics Cengel. Let's say that I bought this book. Let's go back to page 362. So here I think there is, oh, that's the wrong page. Okay, what was the page I needed? Maybe it was bookmarked. It was not bookmarked. Okay, so we need one equation. There's one equation that you use for this. And I don't remember what page it's on. Let's see. These guys are trying to have a sense of humor right here. Read that. Ah ha ha. Not here. Here we are. I circled it. This is the one equation you need to use. Okay, now that's not working. So let's just copy and paste that. We're going to mark it here. I don't know where the origin of this is, but it's in the book, so just write it on your equation sheet. Let's put that, where are we putting that? Man, this stuff is big. All right, let's make that small. Small. Here's equation 1. I think the assumptions, I think we have enough assumptions. It's just an ideal system, that's all. Ideal simple system. Where, and the reason for this is just a Thermo 1 question. And which means, you know, it's just introductory. So erase that to make things clean. Let's erase this. And you're just gonna, I guess I'll erase that. Why not? Oh, come on. All right, there are the assumptions. And this is just off topic a little bit. Isentropic means that the, oops, let's just highlight that. How about that? This means, whoops, what does it say? That the change in S equals 0. So I think this is true. I forgot what big S is and small s is. I think small s, don't remember that, so you got to look that up. S1 equals S2 and lowercase s1 equals lowercase s2. Don't remember what those are. Forgot. I should look in the book. So the entropy doesn't change. And let's draw a ST diagram. So here's the ST diagram. There's a curve. Here's the S-axis and here's the T-axis. So this direction, temperature goes up. This direction, entropy goes up. Which is a little bit strange. Okay. So here, I forgot what this is. Maybe it's a vapor dome. Don't remember exactly. But for this system, we have point 1 and point 2. I think you start here with, is it high entropy? I think you start with high entropy and go down to low entropy. Maybe it's the other way around. I think you go from low entropy to high entropy because originally you start with organized energy. Let's make this smaller, which means the energy, the heat is concentrated. All right. So down here, oh shoot, you know what? I messed up. That's the T-axis. This is wrong. Whoops. Entropy doesn't change. Here's entropy. Does it change? No, it stays constant at this point, right here. S equals C, constant. Because I just said S1 equals S2 equals constant. So S1, entropy level 1, or state 1, is, let's see, you start at a high temperature and you go down to a low temperature. So here's the high temperature and you're going downwards. T equals high. T equals low. L is low. I use a lowercase h for high. And delta T equals high minus low, big minus small, equals is positive. Delta T equals positive, has a positive sign. All right, there's that. That's the side explanation of this. Don't know exactly where this equation comes from, but it's what you use. Now let's say what each of the things are. S is entropy. S is initial entropy. S1 is I don't even know how to spell. INIT entropy. C is, I think, the specific heat capacity. And I don't know why you use the average specific heat capacity. Oh, it's actually average. Heat capacity doesn't change with temperature. What is the specific average? Whoops, didn't want to do that. Don't know why it's average. Think about it. Natural log T2 over T1. This one's initial. T1 is initial, and this one is final. Let's fix that. And strange that I think this is wrong. So the equation that you use here, interesting. Okay, right. So for an isentropic process where the entropy doesn't change, the temperature doesn't change for some reason. Don't know exactly why. Not sure if that is true, because in this case, T1 does not equal T2. So that's a little confusing to me. Somebody let me know why. Hold on, I have a dry mouth. I'm going to go get some water. Get some dry mouth cure. So I'm making this video in order to understand things better. One sec. Sorry you had to smell that. Well, no, you didn't smell it. Sorry you had to hear that. All right, let's erase this stuff. So for some reason we don't use this. Don't know exactly why. I'll think about that. All right, where are we? So there's that. All right, now, next thing you need to find with this equation, let's copy that again. Is we need to know the heat capacity, specific heat. Heat, Q is heat, for the iron and for the copper. So for that, in the book, you look at tables. So let's find that table. So first off, in this book, it's table A3. Use the table and see heat capacity iron and heat capacity copper, average, whoops, for some reason average, AVG. Equals iron, okay, 0.45 kilojoules per Kelvin. And for this, for copper, it's 0.386 kilojoules per Kelvin. And these are from the table. Table values, okay? And what this means is, I think entropy is the amount of disorder. So for every change in 1 Kelvin, or as the temperature goes up by either 1 Kelvin or 1 centigrade Celsius, whatever, then the amount of kilojoules, if there's an increase in entropy, S goes up according to this value, which is dependent on, the value is dependent on the atomic structure, along with probably other factors that are determined through solid state physics. I think these are come from solid state physics. Otherwise, you just measure it in a lab. All right. I'm going to erase that just because that's not, whoops, that's not erase. So for every Kelvin, the amount of energy. Oh, right. This isn't entropy. This is specific heat capacity. So in order to increase the temperature of the object of iron here by 1 Kelvin or 1 Celsius, you need to put in 4.45 kilojoules. Hooray. That's it. I messed up. Not entropy. Not entropy. No. No, no, no. So, over here, this is the equation for entropy, relating entropy to temperature and specific heat. Tn, which is dependent on the initial and final temperatures. All right. So let's go to that table. The table is in A3 in the book. Once again, let's bookmark this. Okay, this is bookmarked, and let's go to page, let's say 1000. Table 17, table 2, table 3E. Where are we going? We're going to table A3, A3E. This is ammonia. Over here, these are liquids. Whoops. Oh no. Did my pen stop working? No, it didn't stop working. Here's some gases. Are they gases? Are they liquid? Gases. They're gases here. And that's table 2E. All right. Table liquid solids and foods. What? That's strange. Where's the food? I guess water is a food. Is ammonia a food? Why not? Let's drink ammonia. All right, so solids, liquids, and whatever the other thing is. It's mercury. It's not mercury. Okay, copper, Cu, copper. Where's C? There's no copper. Next table, A3. All right, here it looks like this is right. Concluded. Copper, here we are. Whoops, wrong thing. There's copper, and what was the other one? I already forgot. And iron. Here's iron. So let's see if that's right. So here are metals, and here are nonmetals. So copper at the average here, you need to linearize it. We're looking for, what was it, 60C? Let's look again. We're looking for 80C. We're looking for this, once again. The specific heat at 80C. Come on, load. So this here isn't 80C. So what's the value that we have over here? According to the book, the values are here. Here are the values. Let's copy that. Copy. Paste. Can't really see that. Let's paste the image. Put that there. So iron. We're looking at copper right now. And it looks like we're looking at the wrong thing. So are we doing CP? Let's see. It's BTU per pound R. That's it. We're in the wrong thing. We're in the wrong appendix. Cubic feet per pound. We're not doing that. We're doing Kelvin. So let's find the right place. Okay, where are we going? What page are we? Here we are. I think here's the centigrade, or the imperial table, which is way better. Look at that. All right, so here we are. I don't know if before it was in centigrade, but if you look at the top, we're at specific heat in kilojoules per kilogram Kelvin. Oh shoot, I messed up. So once again, I messed up here. Is this right? Yeah, this is wrong. So here it's kilojoules per kilogram Kelvin, or kilojoules kilogram times Kelvin, which once again made a mistake. So here, erase that. Let's just add this on. Times kilogram times kilogram. So for every kilogram, in order to raise the temperature, raise by 1 Kelvin or 1 Celsius, you need to put whatever number of joules. 45 joules, 0.45 kilojoules. You need to, I didn't add an E, add 0.45 kilojoules for every kilogram to raise it by 1 Kelvin or Celsius. And 0.45 kilojoules, 1 joule equals, whoops, not 1 joule, 1,000 joules equals 1 kilojoule. That's not kilogram. Equals 1 kilojoule. Isn't that great? So multiply that by 1,000. 0.45 times 1,000. Just add 3 zeros. 1, 2, 3. So 450 joules. Ha, hooray. Put that in a box. Don't really need that. And that's not a box. There's a box. It's actual square. Great. Whatever. All right, so let's look at the table. Here's the table. Copy. Here's the right table. Don't want that. Pasting the image. All right, so copper. Doing this one, copper is 0.8386 kilojoules per kilogram Kelvin. And it's not this, not any of those. We are looking at this area where we're going between 27C and 100C. We're at 80 Celsius centigrade, or not 80 K. K doesn't really matter. You could convert that if you want. So we got 0.386 equals the average. So over here, you just take an estimate. Hooray. So they just use this value. You just use that value. Otherwise, what you could do is average the values. So the middle between, the number between 27 and 100 is 100 minus 27 is 73 divided by 2 equals, what's it, 70 divided by 2 equals 35 plus 1 1/2. So the average temperature, so in between at the temperature, let's make that bigger. If you take an average of the temperatures, at this temperature, 36.5 Celsius, you take an average of these. Oh wait, shoot. Here's the middle. So it's 27 plus 36.5, which is 63.5 Celsius, which is close to 80. So if you want, you can make a plot and find out what the what the heat capacity is. I think CP, is that what it is? I think CP is a solid state versus temperature, because apparently the higher the temperature, the more heat something can hold. All right, man, this is a long question. Oh my gosh. In order to explain this with basic principles, it's really long. So don't need any of that. Ah, right. Let's just go back. Okay. So at this temperature, don't need any of this. This is wrong. Don't need any of this. Do we need that? Why not? Let's leave that there. At 63.5 Celsius, forgot to say that. So at some point it's 80, and at some point down here, wherever it is, wherever you choose, it's 27 and 100. So at some point over here, it's 100. 100C. Point here is 80C. These aren't the correct approximations on the line. Let's choose the right ones. Whatever, we're using blue. So if you say this is 100 up here, and you say over here this is 27, then maybe about there is 80C. About there is 80C. So there's that. Let's erase that, it's too messy. All right. So at 63.5, which is close enough, or actually according to the book, the 27, the CP at 27 Celsius is close enough to CP at 80 centigrade. Hooray. But if you want to find a little bit more accurate CP, you got the average temperature, the halfway temperature between 27 and 100, and the average CP equals, you take an average, CP1 minus CP2, take absolute value just because, divide by 2, which is 38.6. Whoops, that's wrong. 0.386 and 0.393, which is here. The difference, that is, let's count. 1, 2, 3, 4 plus 3. 4 plus 3 equals 7. Hooray! 7, and the average is, so it's 7 divided by 2. Wait, 0.007 divided by 2 equals the midpoint, which is 0.0035. And the units are CP, kilojoules per kilogram Kelvin, per Kelvin. So you add that to the lower value, which is 3.386 plus 0.0035 equals 0.389, whoops, not 0.5. Where you could round that up, I guess. Why? No, you shouldn't round that up. So there. If you want to be more accurate, you do that. Hooray. Leave that. Do we leave that? We're not leaving that. You don't need this either. All right. So here's value 1 that they use, and where's value 2. Apparently for copper, CP changes, or the specific heat capacity changes, and for, what was the other one? Iron. Here's iron, copper, and iron. Iron is 0.45, so that should be right. And is it right? Yes, it is. Here's 0.45, and here's 0.386. Hooray. All right, what's the next step? What is the next step? Next step is use this equation. So the change in entropy of iron is, use the equation. Where's the equation? I think these are big S's. This is big S. And then small s is specific entropy. Which is, or what do you call it? Entropy per mass, which I think is entropy per kilogram, per unit per kilogram. Is it that? I think it's that. So you use this equation oh, come on. Which is little s times mass equals big S. Shoot, did I get that backwards? Apparently, according to the solution, I think that's what it is. So we're using big S, which is, uses the equation, uses this equation. All right, so big S iron equals MC average natural log temperature T2 over T1, which is All right, this is delta S, which is, let's put that over here, which I think is final minus initial. F and I, which is S final minus F initial, which is 80, oh, that's not right, 80 Celsius minus, what is it, 15 Celsius. At the end, final temperature is 15 Celsius, centigrade, whatever. So the delta, no, at these points, so it's SF 15 minus entropy initial 80 equals delta iron, delta S, delta entropy iron, which goes up here. Hooray! Erasing that. Man, this takes forever for a basic question. Let's write down the temperatures. Whoops. All right. Iron equals 30 kilograms. And specific heat is something. Let's move that over. I'll look at it. I'll get it from below. Well, why not? Let's copy it now. All right. Iron. This is iron. Yeah, that's iron. Okay, there we are. So here's the information about the iron, and here's information of for copper. It's 40 kilograms down here, down here. 40 kilograms, and the specific, is it specific? Specific heat for the solid is this. T equals and CP equals that. So let's organize this a little bit more. T equals that. Make it smaller. This all goes here. Let's add another page. All right. Sub all the values in. We're doing iron right now. And that's going to be, whoops, that's not T. I messed up here. Whoops. Mass and mass. So we're doing iron once again. Let's put this down here. Whoops. Clean up, clean up, clean up. All right, mass equals 30 kilograms. Specific heat equals, let's make that bigger, 0.45 kilojoules per Kelvin kilogram Kelvin. Let's fix that. Same thing, kilogram times Kelvin. So that's that. This is this. Now I just need this stuff, which is, man, so fun. T2 over T1. ln T2, which is, what was it, 15? 14? 15 Celsius. Great. 15 over 80 Celsius. Celsius cancels. Let's get a calculator out. That's equal to negative 1.67, estimate to 4. So carry all this stuff through. All the units should cancel. Let's cancel units. So here we have kilograms. Here we have kilojoules per kilogram times Kelvin. Kilograms cancel. And the entropy is equal to something x, some constant. Let's call that constant C. Whoops, not C, constant D. Kilojoules per Kelvin. That's right, units match up. And after you do all that stuff there, everything, this whole thing here goes to, let's see, negative 2.746 equals S, the entropy for, change in entropy for iron. Hooray! Now that's one thing. All right, let's box that. That's boxed. Now next thing you need to find is change in entropy for iron. Do the same stuff. And then hooray, you get the change. It's another negative value, which ends up being negative 0.314. Let's estimate. Negative 0.314. I just rounded. Wow, we don't need to round. 141 kilojoules per Kelvin. Fe. Delta SFE equals that. So it decreases in entropy, which is strange. Okay, we're going to leave it at this. So this is what we're looking for. Let's make everything small. It's small. We do the shrink. All right. Now, next equation is this thing is a system here. Let's copy that. Tappity tap tap. We don't need the figure. Who cares about that? One other assumption is you ignore this. Ignore this. Ignore the ground. Ignore everything about the ground. Whoops, didn't want to do that. So, here's the system. You draw a boundary. Is that what it is? Whoops, forgot. For way at the top here, I forgot to say this. Sorry about that. So step 1, make assumptions to simplify the system. 2, simplify system. That's a funny why. Step 2, think and do some analysis. Analyze. I don't even know how to spell that. Y-S-E. The system. And make sense of all these words up here. All right, and the analysis is heat capacity of the lake, temperature of the lake, delta T lake equals 0, comma, temperature equals 15. It stays at a constant 15. All right, and then what else? So the iron and copper drop temperature down to the lake temperature. When it goes to equilibrium. That would be the lake equilibrium state. All right, there's that. So here's this. And for the system, delta E equals delta E of the system, delta energy of the system equals energy in minus energy out. So let's flip that around. All right. Man, I'm getting hungry. I wonder how long this video is. All right, so the change in energy, right, net energy transfer, that's what this is. So all of the energy types are heat, work, and mass. I assume mass entering or leaving the system. So heat, work, and mass. I think that's entering system, so it would be change in heat, change in what's W? Work. Whoops, not this. Change in work. Change in work and and change in mass. Supposedly this is basic to somebody. I guess it's basic to me. And then over here, the change in energy of the system is change in internal, change in internal, change in kinetic, potential, and other energies. Change in potential and change in, what is it? Kinetic. And internal energy, from my understanding, is if you have something here, you have some solid, some liquid, and some gas. It's the amount of energy of the gas, which is mass times the CP, I think, constant pressure or constant, yeah, if it's constant pressure. And here it's the internal, the innate energy of the solid, which is CP times M solid, which means you have some number of joules, some number of joules for every kilogram. That's how much energy you have in this solid. Pretty sure that's right. Do the same thing for the liquid, do the same thing for the gas. So you find the number of kilograms, and according to the temperature, I think the number of joules is proportional to temperature. So the amount of energy is proportional to the temperature of each of the things down here. That's a big mess. Let's leave that big mess there. So next thing is we have no work. There is no delta V, no volume change. The dot means change. Didn't need that. Whoops. So let's erase it. If no change in mass, because I guess you say that it's an infinite system, infinite mass system. So heat goes out here, and for the lake over here, heat goes into the lake. Here's out, and here's in. So the only things, entropy is related to Q over T. That's the equation for entropy. All right, next thing is, what is it? Next thing is, so fine. So, yeah, we already calculated the entropy, already have the temperature. No, we're looking for the entropy. We're looking for the entropy out. We're looking for the entropy of the whole system. Is that what it is? Ah, right. Okay, so we're looking for the entropy of the system is equal to the sum of the heat over, I don't know, whatever the appropriate temperatures are. Delta T N, for whichever one it is. All right, so we're looking for this. So you need the amount of heat that goes out and the change in temperature. All right. So simplification of this equation is just heat, change in heat, I think. Is that what it is? The amount of heat out of the metals is equal to the change of internal energy of the metals, which is equal to U Fe plus U, so iron, copper. Oh shoot, whoops, my bad. Change in potential, no, change in internal energy of iron. So let's just add a little delta there and a little delta there, and might as well rewrite it. So these things, we already calculated those. We already calculated those, and what do we need? Okay. So what are we looking for? All right, the change, looking for these things in order to find the Q, the heat, which is the thing over here. Let's clean this up. This, we're ultimately looking for this. So the equation for internal energy is mCp delta T. Cp of iron. Let's redo this. Okay, so this thing, internal energy delta U equals that. Shrink everything. Whoops. Whoops. Okay, we're not shrinking everything. Okay, so change in internal energy of iron equals M, let's just say F, Cp F delta T. So the change in temperature, get these values again. Oh man. There it is. And once again, delta T equals 80 minus 15 equals, whoops, I got it backwards. TF minus TI equals 65 Celsius. That's what we're looking for. Not that. All right. So we're doing iron. Iron goes over here. This is 30. Cp is 0.45. And delta T equals negative 65. Whoops, I added an extra 5. Is that right? .45. Let's use units. This is kilograms. This is kilograms per, wait, shoot. Kilojoules or joules per kilogram per Kelvin. And this is delta T, which is temperature. Whoops, temperature. Whoops, which is either Kelvin or Celsius. Or Celsius. Whoops. Or Celsius. Okay. So here's K once again. Per kilogram Kelvin. Kilogram cancels, Kelvin cancels, internal energy change equals kilojoules. So this whole thing here ends up equaling whoops. So here, delta T equals 65 Celsius or 65 Kelvin, which doesn't have a number because, no, not 65 Kelvin, whoops. Whatever the number of Kelvin is, which is 65 plus 273, is it? So delta T equals 273 plus, what is it, plus 15 Kelvin minus 273 plus 80 Kelvin. These things cancel, and the number of Kelvin is 65 Kelvin, which is the same as 65 Celsius. All right, that's enough of that. Oh, great. Oh man. All right, so all this thing simplifies to right, so this is delta U system. Is that what we're doing? Delta U system, which is equivalent to the delta out heat, which is equal to heat out, which is once again equal to, whoops, I got that backwards. It's not really backwards, doesn't really matter. Which is equal to the system, delta U sys equals delta U iron plus delta U internal, iron, nickel, what was it? Copper. So this whole thing is iron. Have that there. That's this. Now we need copper, and you could do the same thing. So delta UF after delta internal F, after putting that into a calculator, ends up being, let's see. Let's put it in a calculator. 30 times 0.45 times negative 65. I think that's equal to negative 877 joules. Kilojoules. Is it kilojoules? Kilojoules. And then the next one, UF equals U copper is you do all this stuff again. Do all this stuff again. Put that in for, whoops. Put all that stuff in for copper. And you end up getting, hold on, let me put it into the calculator. All right, and with the calculator value, you got negative 1,003.6 kilojoules out. Q out equals this stuff. Equals that. That equals that equals that. And the sum of those is negative 180, 1881. Just round it. Who cares? 0.1. Why not? Let's not round it. Kilojoules. All right. So that goes into this equation. Hooray. Make everything smaller once again. Whole page go small. Change in Q sys goes there. Negative 1881. Let's estimate kilojoules over, what is it, 65? Delta T. Delta T equals, was it 65? Oh, whoops, not the system, of the lake. Got that wrong. Equals that over 65, whatever, say Kelvin, which goes to kilojoules per Kelvin equals S. So negative means Q out equals negative is a negative value. Negative value means out. Erase that. This is not a negative because negative means out. And the change in temperature, oh shoot, is not in Kelvin, it's not a delta T, it's a straight T. Oh my gosh, I got that wrong. Oh man. Sorry. So temperature of the lake is 273 Kelvin plus 15 Kelvin, which is 288 Kelvin. Kelvin. And that goes to change in entropy of the lake. .528 kilojoules per Kelvin. So the total entropy change equals the change in entropy of late, whatever, let's leave it late, plus the change in entropy of, what is it, of the iron, plus that change in entropy of the copper, which is I think it's this. Is it this? No, that's not it. Did we find entropy? Where's entropy? Ah, here. Here we are. Number 1, iron, entropy. So there's that. And then where's the other one? Yeah, and then the other one you just do yourself, which is equal to negative 2.746. Whoops, I got that backwards. Okay. This is iron. This is negative entropy, which means, strange is negative. That's weird. A little confused about the sign. Okay, copper is negative 3.141, and the change in entropy of the lake is 6.528. Yeah, I guess when heat goes out, so if you look here, entropy is related to heat over temperature. So if you change these two things, entropy is directly proportional to heat. So if heat goes up, entropy goes up. And if temperature goes up, is that right? Yeah, if temperature goes up, oh my gosh, did I get that backwards? Then the entropy goes down. Strange. What does that mean? All right, let me think about that. I can't pause. So heat. Temperature goes down. Okay, that makes sense. So when something is cold, temperature goes up. Something heats up, entropy goes down. That's strange. What? That is really strange. Well, there's that equation. So the lake gains heat, the lake gains entropy, and each of the blocks of iron lose entropy. Okay, and if you add all this stuff together, you get the value 0.642 kilojoules per Kelvin. So the entropy goes up. Entropy increases. in the whole system, which makes sense because entropy always, whoops, entropy is not that. Entropy always increases and never decreases, you know, same thing. Or it could stay the same. So S initial is always less than or equal to the final entropy. So this, the initial entropy always increases. They're done. Oh my gosh, why did that take so long? If you look over here, oops, that's the wrong thing. That's wrong. Oh man, I'm going crazy looking at the copy. Is this right? That's wrong. Is this right? That's wrong. Here we are. So reviewing. Step 1. Make some assumptions to simplify the system. Step 2. Gather the properties of the system. Step 3. Do some analysis. Step 4. Find relevant equations, which is that. In order to find the entropy. Because it's asking about entropy. Total entropy change. Find the entropy. So there you have don't have this, do have this, do have this, do have that. So with all of these, you get this. And then afterwards, do an energy balance. And then afterwards, use this equation down here. Hooray, done. For this simple problem, look at that. Did that make any sense?